Hey there. In this quick guide, we're going to demystify CPU scheduling problems. I'll give you a clear, step-by-step method to solve them just like you would in an exam.
So if you see a table like this with arrival times and burst times and your brain just kind of shuts down, don't worry, you're not alone. But honestly, it's just a puzzle with a few simple rules. By the end of this, you'll see exactly how to solve them. All right, let's get into it.
Okay, so here's our game plan. We'll kick things off with the basic rules and formulas you absolutely need to know. Then, we're going to walk through 4 of the big scheduling algorithms, one by one. First come, first serve, shortest job first, priority, and round robin. And to wrap it all up, you'll get a chance to try one yourself, and we'll recap the key takeaways.
All right, first things first. Let's get our key terms and formula straight. Think of these as the building blocks for literally everything else we're about to do.
Okay, let's lock in these terms. Arrival time, or AT, is just when a process shows up ready to go. Burst time, BT, is how much CPU time it actually needs to finish its job. And completion time, CT, is the exact moment it's all done. Now, the 2 formulas you have to burn into your memory are these. Turnaround time is simply the completion time minus the arrival time. It's the total time the process spent hanging around, from start to finish. Then you've got waiting time, which is just the turnaround time minus the burst time. This tells you how long the process was sitting in the queue waiting for its turn. We're going to use these 2 for every single problem, so make sure you've got them down. Oh, and our tiebreaker rule is simple. If burst times are equal, we pick the one that arrived earlier.
All right, let's kick things off with the easiest one of the bunch. First come, first serve, or FCFS. And it's exactly what it sounds like. We just process the jobs in the exact order they show up.
So, here's our first problem set. We've got 5 processes, P1 through P5, each with its own arrival time and the burst time it needs. What we're going to do now is build a Gantt chart step by step just based on who got in line first.
Okay, let's build this Gantt chart together. We start at time 0. Who's in the ready queue? Well, only P1 has arrived, so it gets the CPU. Its burst time is 4, so it runs from time 0 all the way to 4. That means its completion time is 4. Simple enough. Now, at time 4, we stop and look at our queue again. By now, P2, P3, and P4 have all shown up. Since this is first come, first serve, who do we pick? The one that arrived earliest out of that group, which is P2. P2 needs 3 units of time, so it runs from 4 to 7. Its completion time is 7. Okay, now it's time 7. Who's next in line? P3 arrived before P4 and P5, so it's up. It only needs 1 unit, so it finishes at time 8. Next up is P4. It runs for 2 units, finishing at 10. And finally, P5 gets its turn, running for 5 units and completing the whole thing at time 15. And there you have it, that's our Gantt chart. From here, calculating the turnaround and waiting times is just plugging numbers into those formulas we talked about.
So to wrap this one up, we just calculate the averages. Add up all the waiting times, divide by the number of processes, in this case 5, and we get an average waiting time of 3.8 milliseconds. Do the same thing for the turnaround times, and we get 6.8. Think of these numbers as our baseline. We'll see how other algorithms compare.
All right, let's move on to our next algorithm, shortest job first, or SJF. Now, the key rule here is that we always choose the process with the shortest burst time, but only from the pool of processes that have actually arrived and are waiting in the queue. This is the non-preemptive version, meaning once a job starts, it finishes.
Okay, here's a new set of processes. The burst times are a bit different this time. Let's apply that SJF logic and see what happens.
Let's build the Gantt chart for SJF. Again, we start at time 0. Only P1 is here, so it's the only choice. It runs for its 4 units and finishes at time 4. Now this is where SJF gets interesting. At time 4, we look at who's arrived. P2, P3, P4, and P5 are all waiting in the ready queue. Now we have a choice to make. We look at their burst times. P2 is 3, P3 is 1, P4 is 2, and P5 is 6. Who's the shortest? That's P3 with a burst of just 1. So P3 gets to run next, from time 4 to 5. Great. Now it's time 5. Who's left in the queue? P2, P4, and P5. Their burst times are 3, 2, and 6. The shortest is P4, so it runs for 2 units from 5 to 7. Now we're choosing between P2 and P5. P2's burst of 3 is shorter, so it runs next, finishing at time 10, and that just leaves P5, which runs last, completing everything at time 16.
And just look at that result. Our average waiting time has dropped to 3.2 milliseconds, which is a nice improvement over the 3.8 we got with FCFS. This is why SJF is often called optimal. It's mathematically proven to give the minimum possible average waiting time.
Of course, the big catch in the real world is you almost never know the exact burst time of a job before you run it.
Now, it's super important to get this distinction between non-preemptive and preemptive scheduling. What we just did was non-preemptive. Once a process like P1 started, we let it run to completion. But there's a preemptive version, often called shortest remaining time first, or SRTF. In that world, the scheduler is much more aggressive. If P1 was running and had, say, 2 milliseconds left, and a new process P3 arrived with a total burst time of just 1 millisecond, the system would immediately preempt P1. It would pause it and run the shorter job, P3, first. It's constantly reevaluating, which makes it more responsive, but also a lot more work for the CPU.
Okay, next up, priority scheduling. This one's pretty straightforward. Each process gets a priority number, and the CPU always goes to the process with the highest priority. And just for our examples, we're going to say a lower number means a higher priority.
So here's our new table, and you'll see we've added that priority column. Let's walk through this one. At time 0, it's easy. Only P1 is available, so it runs. It needs 4 units, so it finishes at time 4. Now, at time 4, we check our ready queue. P2, P3, P4, and P5 have all arrived. This is where priority comes in. We look at their priority numbers, 5, 7, 2, and 1. Who has the highest priority? Remember, lower number is better. That's P5 with a priority of 1. So P5 runs next. It needs 3 units, so it finishes at time 7.
Okay, now it's time 7. And in that time, P6 has also arrived. So our queue now has P2, P3, P4, and P6. Let's check their priorities. 5, 7, 2, and 6. The highest priority here belongs to P4 with a 2. So P4 runs for its 2 units, finishing at time 9. Next highest priority is P2, so it runs, finishing at 14. Then P6 runs, finishing at 20. And look who's left. Poor P3, with the lowest priority, finally gets to run, finishing way out at time 21. And this highlights the single biggest drawback of this method, something called starvation. A process with a low priority might get stuck waiting forever if there's a constant stream of higher priority jobs coming in.
And now for our final algorithm, one that's designed specifically for fairness, round robin. This is a preemptive algorithm. The idea is to give every process a small slice of CPU time, called a time quantum, and then move on to the next process in line, cycling through them over and over.
So here's a round-robin problem. The most important number on this slide is the time quantum, which we've set to 4 units. This is the maximum amount of time any process can run before it gets kicked off the CPU. To keep track of everything, we're also going to need a new column for remaining burst time.
Okay, let's trace this one really carefully. Our time quantum is 4. At time 0, only P1 is in the queue, so it runs, but only for the time quantum of 4 units. So from time 0 to 4, P1 is running, it had a burst of 8, so now its remaining time is 4. It gets sent to the back of the ready queue. Now, by time 4, all the other processes have arrived. The next process in our queue is P2. Its burst time is exactly 4, so it runs from time 4 to 8, and it's done. It leaves the system completely. Who's next? P3. It runs for the time quantum of 4 from time 8 to 12. Its burst was 9, so its remaining time is now 5. It goes to the back of the queue. This cycle just keeps going. P4 runs for 4, then it's P1's turn again for its final 4. As you can see from the chart, it creates this interwoven execution. This is great for fairness and responsiveness, but look at those completion times. They tend to be a lot higher, which means waiting times are higher too. It's a classic trade-off.
Okay, you've seen me walk through all 4 of these. Now it's your turn to give it a shot and apply what you've learned. Grab a piece of paper and a pen. I want you to try and solve this simple problem using the first-come, first-serve algorithm. Your goal is to draw the Gantt chart and then calculate the average waiting time. I'll give you 20 seconds. Ready? Go.
Instrumental music plays for 20 seconds.
All right, time is up. The correct average waiting time for that problem is 4 milliseconds. If you got that, fantastic job. If you didn't, no worries. Just go back and review that FCFS section. And no matter which algorithm you're using, if you follow these 5 rules every single time, you'll nail these problems. Rule number 1 is the absolute most important. Always, always check the arrival time first to see who's actually in the ready queue. Be methodical, draw the chart step by step, and you'll get it right.
Of course, the best way to really get good at these is just practice. So we've put together a downloadable worksheet for you with more problems and the full solutions. You'll find the link for that in the description below. Thanks so much for watching.